Hello everyone, we're going to do this fall 2024 exam together. Okay, so the first thing you do is to write down your name. I'll write down mine. And circle the section that you're in. Okay, so first question. You don't have to justify your answer to get full credit. So it's good to write down your justification and to check your answer throughout the practice. Okay, so now we have vector A, B, and C as below here, and the lengths are given. So for A, circle the vector that best represents this vector. So we drop the picture. We have 1/2 of A, and negative B. So you put this parallelly to here, and then you add the vector together, head to tail. This is your vector. And as the picture shown, it's probably this vector, S. So the answer is S. Okay, the next question. To circle the vector that appears parallel to projection of B onto the vector A. So this vector would be parallel to A. Now, which vector looks parallel to A? I think it's quite clear it's this W. So the answer is W. Although this picture do look like the A and B they are orthogonal, but we don't know. So the best answer to choose here is still W. Now circle the number closest to inner product of A and C, which is the length of A and multiplied by the length of C and cosine theta. And this theta is the angle between them. Okay, and we know their lengths are 1 and 2 respectively, so 2 cosine theta. Now we have to approximate this theta. Theta is approximately, I would say, pi over 4. So cosine pi over 4 is 1/2, 1 over square root of 2. So 2. This gives you square root of 2. And you can check other answers that might be close. But for 1, your cosine theta has to be close to cosine pi over 6. So in that case, it'll be around, C will be around here. So it's like this. And for the case of square root of 3, your cosine theta is approximately cosine pi over 3. So it's okay. I don't think this is the case. Okay, so you want to be more careful. You can check the other answers that are close to square root of 2, but you can just go with your instinct. That might help to speed up your process, and you can check later maybe. So this can be checked later, or you can check it here. Now D, a non-zero vector n is pointing directly up out of the page. Circle the best description of the B cross product C. So we know B cross product C is pointing out of the page. It'd be a normal vector. So it is parallel to n. And we have to determine it is either a positive one or a negative one. But we know B is pointing towards C clockwise. So it is a negative something power of n. Okay, we can move on. Now we are in this question 2. So parts A and B, they're not related, but for part A, you have 2 questions. Now find the area of the triangle with the vertices P0, P1, and P2. There are several ways to approach this, but let's take a look for the second question. Find the equation of the plan containing the points. So we do know if we find a normal, like this, then this plan will, the equation of the plan is this plus some constant, let's say alpha. So alpha is a constant. Okay, so now it would be convenient if we know what is n. And we can also use this n as an ingredient to solving the first part. So let's see. If you have a triangle like this, P, okay, then you can compute the area of the parallelogram. So the area, and if you divide this area by 2, you get our area of the triangle. So area equals, for example, the cross product of these 2 vectors, right, as we see. And this vector is exactly parallel to our normal vector. Okay, so we can compute this cross product, and it would be convenient to know this for the second part. Okay. Now find the area. So we first compute this vector, which is -1, -0. Okay. And P not P2 is 2 -0, 2 -1, 0 -3, get 2, 1, -3. Now we compute the cross product. write down the determinants. 1 minus 3 minus 1, 2, minus 1, minus 1, 2, 1. Okay. So we get 3 plus 1, which is 4, and minus 2 minus 3, which is minus 5, and minus 1 minus 2, no, minus 1 plus 2, so it's 1. Oh, okay, computing this, the absolute value, you get the square root of these numbers and then take square root. That's 42, square root of 42. So the answer, the area of triangle is, don't forget to divide this by 2. Okay, and now it would be very convenient to compute the next question. So you have ABC can be 4, negative 5, 1. So the equation is this, and plus an alpha. And this equals an alpha. How do we determine alpha? You just plug in either P0 or P1 or P2. So we choose to plug in P0. You get 4 times 0 minus 5 times 1 plus 3, which is minus 2. Yep, that's our constant. Okay. Yeah, what about the next question? There is a formula. So you plug in this point in this equation, plus 1 plus 2 minus 6, and divide it by the length of the normal vector. So you get 2 plus 1 plus 2, which is 5 minus 6. And here's 4 plus 1 plus 1, I guess 6. So here you get 1, right? So 1 over square root of 6 is our answer. For second question, find a point of intersection between this plan and the line with direction vector 2, 1, 1, and passing through this point. So the point, we can find a point. It must satisfy that line equation, which is minus 2 plus 2t minus 2 plus t and 0 plus t. So like this, and you plug in your t to this equation. You get 2 6, so minus 4 plus 4t minus 2 plus t. There's another t, like this. And in total, you get 60 is 12, which implies t is 2. Okay, now you plug in this 2 back to the point P. So P is minus 2 plus 4 minus 2 plus 2. 2. The answer is 2, 0, 2. Okay. Now, the third question. A particle moves with this velocity. Suppose the particle's position at time pi is this point, okay? Then we have to find the parametric equations for the tangent line at t equals pi. Okay. Yeah, so we have to find the tangent line that passed through this the point of the position when t is pi. So the tangent is phi of pi, which is, or we can use angular bracket, because sine pi squared. So this is okay. Now the tangent line is, so you have the point, so your x equals pi, e to pi, plus your tangent, so as e to pi, and y is 1 plus as z is 0 plus is pi squared. Okay, this is our line. Oh, I guess I did something wrong here, because sine pi is minus 1 instead of 1. That's 1 minus s here. Okay, good. Whereas ranges through the whole real line. Now, what is the particle's original position at t equals 0? So we do know the position at time pi, and we want to find the position of this particle at time 0. So this is exactly the integral of vt dt, right? And this is a vector, so we're going to do this separately. Integral bracket e pi minus e0, and for this it is sine t from 0 to pi, which is 0. And this is t cubed over 3. So pi cubed over 3. Good. Now p0 is p pi minus that vector, e pi 1, 0, minus okay. So there's minus here, so we get 1 minus pi cubed over 3. Okay. What about the distance traveled by the particle from t equals 0 to t to pi? Okay, the good thing is we don't have to evaluate this. So what do? Distance is the integral of speed from your time interval. So this is square root of the, you add up the cubed, the squared, cosine square t plus t to the 4th. Okay. Good. We can move on. So you have level, you have, sorry, you have level curves for this function with k equals 1, 2, 3, 4 to 6. And here k equals 1 is the innermost inside, and k equals 6 is the outermost. So they're sequentially in between. Sure. Okay, so which one is larger? F of p or f of q? So identify f of p is here and f of q is here. So these are the level curves. And we can observe that as x increases, the value will increase, right? Here, this will increase, this also increase, and here it also increases. And the same thing is true for y. So as x increase and y increase, the value is larger. That's what we know. So I think we've already know the answer. Fp is less than Fq because f of xy is increasing with respect to x and y. With both x and y. And how do we explain? It's at the level curve q belongs, it's outside of the level curve of p. So level curve of q is outside of that of q, that of p. Okay. Now we have to determine whether f of x or f of y, they're positive, negative, or 0 at point r. Here, as we know, the function is increasing with respect to when x and y, they're larger. So fx and fy, they are both positive, then you have to explain. So I guess that's the same argument. Or you can say or just stick with the original argument. So f of x and y there, this function is increasing with respect to both x and y. Right. And yep. Okay, what about f of fxx and f of fyy? So we have second derivatives. The signs are at q. So we're now at q. So for this, you can either compute directly, or you can see from the level curve. It's so fx so fxx is the second derivative of f with respect to x, and as we can see, here it goes much more rapidly in this direction. So fxx is positive, the same as for fyy. It goes more and more rapidly. The space is decreasing. So we can tell from the spacing of level curves. Oh, okay. Or we can try to compute that directly. Yep. Next question 5. Find a vector function that represents the curve of intersection. So we have to find the curve of intersection of the plane and the hyperboloid. Okay, what do we do here? Okay, there is only one z here, so it's probably a good idea to replace that z with 3 minus x, which is from the equation here, and see what we get. Because in this case, you'll get an equation that only involves x and y. So we'll get a curve of intersection. Now 2x squared plus y squared plus 2y plus 3. Okay, so you get, I guess you can first put the x term together, right? Like this. So y squared plus 2y minus 6 equals 0. Minus, maybe you don't have to plus y plus 1 equals 6, and also we have the extra 9 because of the square there, and then extra 1. So 6 plus 9 plus 1, which is 15. No, it's 16. Sorry. Okay, now you get a circle of radius 4. But you have to find a vector function. So that means okay, now we know what are the x and y, and we can plug in this x and y and get z from the equation of the plan. But first, let's find a parametrization for the curve for our circle. Which is because of that radius 4 here, you can write it as this, and minus your center of the circle, right? For t between 0 to 2 pi. Okay. Now the parameterization of the vector function we want is we plug in the x and y. And don't forget z equals 3 minus x. So we get 6 minus 4 cosine t. Also for t between 0 and 2 pi. Okay. Good. Now we compute derivatives, partial derivative of f with respect to x. Okay. So we can compute directly and use chain rule, but let's simplify this as log 3 plus log x minus log x plus y squared. And now it's easier to compute. So you get x, 1 of x, and x plus y, 1 of x plus y squared. Good. What about next? You consider the surface as x squared plus y z cubed equals z. And find partial z, partial y at the point. Okay, so let's compute first and plug in this point. It's not as simple as the previous one because we have z both at the left hand side and the right hand side. So partial z, partial y. So we're differentiating the whole stuff with y equals this, right? And the left hand side you get z cubed plus, so we're first differentiating against y, and then we differentiate the z squared, z cubed, you get this, and don't forget partial z, partial y. Okay, let's try plugging this 0.101. So we have 1 plus 0. You plug in y equals 0, get 0 here, and then partial z, partial y. Okay, so our answer is 1. What about if you do twice partial derivatives? So we do the same thing again, and you get so sorry. If you already know from above, we have this is the first derivative. We just differentiate that again with respect to y. Okay, so on the left hand side we get z squared. Here you don't get anything, then you first differentiate with this y. And partial z partial y plus y 6z partial y plus y cubed 3 squared partial squared z partial y squared equals this. Okay, let's try plugging 1, 1, 0, 1. So here we have 3 times 1. We computed this earlier. So from the first part we know this is 1. And we also know this. But if we plug in y equals 0, you don't have anything here. It goes to, it's 0. And it's 0 also here. So the answer is 3. Is it? Okay, I checked. It's not 0. Oh, sorry. We have another term here, actually. Sorry. You have to differentiate with your differentiate again with that 3z. No, it's squared here. Oh, is it not? No, it's, I think we're missing a term here. No. So oh, I guess I do miss this term. As we said earlier, we have to differentiate y, but I didn't write that down, which is a terrible mistake. Let's edit here. Then now we get the answer. So the answer is 3 times 1 plus 3 times 1. Okay, you have to be very careful because you better count how many terms you should get from the product rules. So you should have 4 here because you should have 4. Okay, so the answer is 6. Okay, sorry for that. Okay. Now we're here at the 7th question. So you don't have to provide your justification, but still, it's nice to justify your answer. You might get partial credit even though your answer could be wrong. So we have to consider the function f, which is sine of x plus y with this absolute value. Now identify which surface is the graph of f. So let's see if x plus y is, say, 0, then it's probably we have z here and x here, y there. So x plus y equals 0 is in this direction. Okay. And when that happens, the value is 0. You can see it's indeed 0 for this case. And I don't think we get 0 for the first one. And what about the third one? Okay, it's not 0. So it's probably the second one. So sine 0 is 0. Okay, and now let's see. So, and another thing to look at is when x plus y equals k, then this value is sine k. So it should be a constant along the direction like this, which is exactly 2. We don't really see that phenomenon here at 1, right? Okay. Well, I guess it is the case for 3, but you have to notice that sine is periodic, so we can exclude 3 and 1, so the answer is 2, the second graph. Okay, so for the final question, not the final question, actually we have more, but for part B, we have a particle moves following a trajectory like this. We have to identify its trajectory. So you have we have to observe the behavior of this trajectory. So for t, when t increases, your t sine 2t is increasing, provided that your t is between these numbers. But yes, maybe you can, no. Yeah, let's stick with this. And for even larger t, this sine 2t can be either either positive or negative, but it shouldn't be bounded within a region. So let's see. Could it be 2? Not likely. It only has values in the positive z's. Okay, we can start with the obvious one. This one stays above the xy plane. What about the third one? It stays below the xy plane. So shouldn't be this one either. No, actually it stays on the xy plane. So this is less likely to be the answer. We can exclude this. What about the fourth one? Okay, it looks to me that it has positive z's and negative z's. We can really tell from the information of the positivity of z's. What about well, because we can zoom in a bit. So now it's clear. So for this curve, it always stays in a xz plane. The y is never non-zero. Well, the y is always 0. But for our case, the trajectory does suggest the possibility of y being not 0. So not fourth. Okay, I guess we're left with the first one, which it travels like all the possible places between, like it goes up and down and to the left, to the right. It does look like this trajectory. Okay, so the answer is 1. Now, finally, the final question. Okay, so again, you can choose if you want to justify your answer. But I would recommend doing this. So, if the level curves are all circles, then the graph must be a cone. Okay, nope, because you have like y equals x squared. Or instead we should say f of xy equals x squared, so that it should look like x squared is like a paraboloid. So somewhat looks like this. Right. Or you just draw a paraboloid. So the answer is false. Let P be a plan with normal N and L is aligned with direction V. Assume that you have the inner product of normal and this V is non-zero, then L must intersect with the plan P. So you have the plan P is normal. L is aligned with direction B. So L is aligned with direction B. Let's say like this, L, because that direction is, they're not perpendicular. If they're perpendicular, L could be like this and lies above the plan P. They never intersect. But because of this condition, then they should intersect somewhere. Like this, for example. So now, now we have A, B, C. They're non-zero three-dimensional vectors. If A and B are orthogonal and B and C they're orthogonal, then A and C are parallel. Okay, we're in 3 dimensions. So let's draw a simple counterexample. You have A, B, C. They are they're on coordinate planes, x and y and z. So like this. Then they're all orthogonal, but A and C they're they're all pairwise orthogonal. So the answer is false. And now we have two curves. They intersect at a right angle at the point at the origin. So let's see. We have to find the velocity. So velocity R. I have 2, 3, 0, and 3 minus 2, 0. Okay, they're orthogonal, yes, at time 0. So, yes. Okay, next. If we have a parametrization of a curve, gamma t, whose tangent vector are all orthogonal to 0, 0, 1, then this R is orthogonal to 0, 0, 1 for all t. Okay. I don't think that's the case, you can come up with counterexamples like gamma t can cross 0, 0, 1 plus some, for example, t. Then your tangent vector would be 1, 0, 0, always, which is orthogonal to 0 and 0, 1. And this curve pass through 0, 0, 1. So it's not orthogonal. It's not orthogonal to 0, 0, 1. So false. Okay. Now, if R of t it parametrize the curve and satisfy our t inner product with our prime t is 0 for all t, then this curve lies on a sphere. Okay, for me, it somewhat looks like the derivative of this stuff, except we're missing a 1/2 in front. So if this is 0, then R of t squared is a constant. No, it should be, it's not R, it should be the norm of RT squared. So, I'm sorry, so RT squared is a constant. That means RT belong to the sphere with radius, right? Yes. Yeah. Oh, not this is a ball. Or we can write this. So R of t lies on a sphere of radius c. Okay, this concludes the exam. Okay, now good luck with your exam next week. Thank you.